I would like to welcome you back to our class after the most needed 1 week of break. From now on, we will be going over a couple of problems and apply some of the concepts that we've been learning from the past couple of months in order to be prepared for the test, and that is on May 14th at 1 o'clock in the afternoon Pacific Standard Time. Also, there is a PDF copy of the solutions for the assignments or problems that I will be giving you. In this case, this is the assignment given to you, like assignment number 1 before you went on break. If you have the capability to print or you do have a printer at home, I would suggest that you print out all of those solutions, all of the notes, put them in a file, organize them, because it can be used during your tests. Yes, you heard it correct. The test is going to be open notes. So you are able to use your notes. However, having your notes, if it's not organized and you have not used them, is useless because it will not serve you the reason why you have the notes, and that is to have the information on how to solve specific or answer specific questions. So without further ado, let me go over the questions. And this assignment composes of 2 questions. After this video, there is another video that is attached for today's lesson, and that has something to do about torque and angular momentum, and some problems and assignment that is due by the end of the day. Um, Again, I would like to welcome you back, and still do apologize about my voice, as my voice, I haven't fully regained my voice yet after being sick for 4 weeks now, and still counting. So let's go to the first question. First question is written as is. So the challenge is to make the rope horizontal. So the problem goes, or the scenario goes as on. Two people standing on equal height buildings are lifting a box of mass M between the buildings using 2 ropes. The people keep the 2 ropes the same length between their hands and the box so that both ropes makes an angle theta with the vertical. So the illustration is on the right side. This words or the description is actually an explanation of the diagram on the right side. So if we go to the next page, it will give us, or it will ask us the first question. So the first question right here is on the dot below that represents the box. So that is the box. Draw and label the forces exerted on the box at one moment in time when the box is at rest. By the way, I would like to mention it that since it is expressed that the incident happened one moment in time, so it means for every frame of time the box is not moving. So it will be more simple for us, it's easier for us if we look at the diagram again. So there's 2 sources of forces, or actually 3 forces. First of all, we have the force because of the mass. We have the tension of the rope by this human on the left side, and then another human on the right side pulling and exerting the same amount of tension or force. So let's draw the free body diagram on the dot. But since we don't know, how would we call the human on the left side or the person on the right side? So let's just assume that the person on the left side is person number 1 and the person on the right side is person number 2. Then we can use the different designation. And then of course this is M And what is the first force acting on any object? Since any object contains mass, therefore it is also simple or most appropriate for us to say that gravity always exists because we're on the surface of the Earth. So the first force caused by mass is force of gravity, and it's always towards the center of gravity of the planet. Next, we have the first tension exerted by the human on the rope as the mass is attached at the lower end of the rope. The second tension is tension produced or exerted by the second person, and that is force on the right side, and that is force of tension number 2. So this is force tension number 2, representing our force tension number 2. Force tension number 1 is represented by force tension number 1. And of course, the mass, which is always subjected to gravity, and that is what we call force of gravity, or also known as weight. It seems like the diagram doesn't have any other force, so therefore this is your final answer, that there's one force acting on the first one, first tension that is upward, and then the second force that's going upward, which is tension number 2, and then the force of gravity that is towards the center of gravity or downward. So now let's move to the next bullet or next question that is being asked in this scenario. Scenario B, or question letter B. Derive an expression for the magnitude of the tension Ft in the two ropes in terms of m, theta, and some fundamental constant. Fundamental constant may include g, uppercase G, and all of those constant that exist because we of certain condition. On this case, we only need constant g, which is acceleration due to gravity. Moving, how do we derive this? Moving on, first thing is to make sure you have our free body diagram. Free body diagram is drawn from the previous question. And since from question A, it represents the box at a moment at rest, again, let us assume that the forces acting on the y-axis is equated to 0. Okay, so let's just assume that the force acting on the y-axis is also 0. And likewise, as I was speaking about it, the angle theta was also indicated. So this is the part where you can include all of those other information as part of your solution, as part of your scratch. This is for you. Okay, this is for you to absorb and come up with the answer. So now, since the diagram from question, again, let me just repeat, is represented by the box at the moment of time is at rest. Therefore, the summation of forces on the y-axis, which means the vertical axis, is 0. So it means that force going up is equal to force going down. That's why there's no change in position. Now, let's represent the summation of forces. What is summation of forces? Summation of forces is force, all of the forces, force of T sub 1, T sub 2, and then force of gravity equals 0. Now, positive for everything that is going up. So tension number 1 is positive. Tension number 2 is also positive. Tension, there's no more tension. What I meant is force of gravity is going down. So that is negative. So everything that's going up is positive. Everything going down is negative. But in this case, there's only three forces, so that's why we're already done with our of setting up the equation. Information that you should know is that the angle is identical. Right here, ladies and gentlemen, the angle is identical as I'm highlighting those sections. The angles are identical. So if the angles are identical, it is also safe for us to assume that the tension over here, tension number 1, is the same as tension number 2. They're identical. But since the angle are also measured on the vertical axis, so therefore we should use cosine as our function to multiply to denote that this tension is subjected to components. So the component, since the angle is measured on the vertical axis, we should use the function cosine theta. And also, Fg is always equivalent to whatever the mass is multiplied by the constant g, which is the acceleration due to gravity. All we have to do now is plug in these values to the first equation that we have. By plugging in the values, now we have Ft cosine theta because of this, plus, let me just denote this. So Ft cosine theta, because this is represented by Ft1, because Ft1 is also equivalent to Ft cosine theta as shown over here. Tension 2 is the same. So I can just change Ft sub 2 or tension 2 into force of tension cosine theta minus Fg. But Fg is right here. So I will plug in the value of Fg because Fg and Fg are here. So I'll pause a bit so you could absorb it. Now that we have plugged in all those information, so what I'm going to do, I'm just going to erase it so it doesn't get too confusing to all of us. Now let me clear it. So if you want to go back later to figure out where did it go, where did it come from, you can always go back and check. So the next step is to just simplify it from math class. This is like terms, Ft cosine theta. It's like having your x. So now we can just simplify it to Ft cosine theta and move our negative mg to the other side of the equation from negative to positive. And then so on and so forth. Let us divide both sides by cosine theta. So therefore, this is your final answer. So do not forget to draw a box around your final answer so it's easier for the person who is grading it. Okay, so it's easier for the person who's grading it to know what is your final answer. You don't need to specify the units because units was never mentioned. So because this test is only like 45 minutes, it's more of showing what you know and not too much on the details of it. So as we move on to the next slide, which is the last question in this presentation or last question for this problem, which is supposed to be the 15-minute question as part of your test. It says over here, the graph shows the values of sine theta and cosine theta for angles between 0 degrees and positive 90 degrees, right here. The two people notice that as the box rises, let me just highlight, as I mentioned, so this is your cosine theta and sine theta graph. So the two people notice as the box rises at constant velocity, the force they must exert on the ropes becomes greater and greater. Oh, so as it goes higher, becomes greater. And they cannot make the ropes horizontal no matter how much force they exert. Use your equation from part B and explain why the people have these experiences. Again, keep it simple. Okay, here is an example solution. Remember from the previous solution that the force of tension is mg over 2 cosine theta. And then on this graph, as cosine theta or theta reaches 90, it turns to the value of cosine theta is 0. Okay, so as the people shorten the ropes, the angle theta becomes larger. Larger as in closer to 90 degrees. Since the tension, which is Ft in the rope, is proportional to 1 over cosine theta. Again, let me just rewrite it here. What is your Ft again? Ft is 1 over 2 cosine theta, or actually it's not 1, but it's mg cosine theta. Sorry for that. So it's mg over cosine theta, or we can just rewrite it this way. Oops, I said rewrite it this way. So let me erase, do it again. So that will give us mg over 2 times 1 over cosine theta. So this will be another way on how to represent your answer. So that's from the previous page. So as we notice, 1 over cosine theta. If cosine theta or theta reaches to 90, as the angle gets larger, cosine theta approaches 0. And 1 over theta is infinity. So if the angle were to be 90 degrees, the tension would have to be infinite. Okay, guys, the tension should be infinite. Since infinite tension is impossible, the people can never make the ropes horizontal. Okay. So here's one of those basic explanation that you may use, okay, applying whatever you learn from different classes, from mathematics all the way to science class. So these are the different solutions or different parts of steps to answer question number 1. So far, we are in good hands in terms of timing. It's supposed to be completed in 15 minutes. 15 minutes. So let's move to the next slide. And again, you can always go back and look at the videos, pause and try to analyze on your notes what is it and how did it came up to the solution. So here's the question. Force versus distance. So a constant force F is exerted on a dart of mass M. So here's our dart with a mass M. So you create force. So you exert force going inside this thing. In the horizontal direction as it moves through the tube of length L. Again, length L of a tube. The tube is situated a height h above the ground, so right here. How high? Upon exiting the tube, the dart travels a horizontal distance x. Oh, okay. So it travels downward and at the same time travels sideways. This is a concept called projectile motion. And it travels at x distance before striking the ground, as depicted at in the diagram at the right. So here's a diagram. Now let's take a look at the first question. Suppose students experiment with a tube in a variety of darts. Some darts have higher mass, others than others, but are the same aerodynamic shape. So it means the same shape, maybe different material, it's lighter, assuming air resistance is negligible. Okay, so negligible. So assuming that it is negligible right here. Should the student use a dart with a large mass or small mass to launch the dart the farthest distance possible? So let's figure out what will be the value of the mass in order to produce the farthest maximum x or horizontal distance. It is common sense and most of you will answer small mass, x. So this is the correct answer, x. But now, it doesn't say just give me the correct answer. As part of your test, this is the 25 question test. Briefly explain your reasoning without manipulating equations. So we're not solving problems, but this time they want to know your ability to explain certain problems or your reasoning. So let's take a look at the scenario. If this is the tube, and here's the dart inside, and here's the length of the tube, we have to apply force, so negligible air resistance. So the first concept is that the dart will experience the same initial force while inside the tube as it travels the length of the tube L. So concept number one. So always remember, it says in the problem, some darts have higher mass. Should a student use a dart with a large mass or small mass to launch the dart the farthest distance possible? Since we're using constant force, okay? Constant force applied, constant force is applied, and this is our first concept. The dart will experience the same initial force, same force. So whatever we do, if the mass is small, the mass is big, we have the same F. What will happen when you apply force? The dart will leave the tube. It's like a blowgun principle. Okay? Blowgun principle. Concept, the dart will experience the same initial force while inside the tube as it travels the length of the tube L. Now, second concept that we must remember is that according to Newton's second law of motion, it states that the net force is equivalent to the product of the mass and acceleration, or acceleration is net force divided by the mass. Therefore, we can always make this conclusion that the smaller the mass, the greater the acceleration, and resulting in a greater speed as the dart leaves the tube. Again, so now if the mass is less, it will leave the end of the tube with a greater velocity. But why? Why will it produce the greatest velocity as it leaves? Because of the equation that we've been using, that acceleration or the final velocity is always dependent on the length or the displacement or the distance an object is accelerated. But since the force is kept constant, the length of the tube will be kept constant. So the only way that we can increase the acceleration is to decrease the mass, resulting in a greater acceleration according to Newton's second law of motion. Now, concept number 3 that we must remember. According to the concept of Galileo, the mass of the dart is irrelevant once the dart leaves the tube, because falling object will reach the ground at the same time when released from the same height regardless of the mass. Remember the experiment when we dropped two different objects, a piece of paper and a textbook. As long as there's no air resistance, and the problem states air resistance is negligible, it's right here. Oh, let's change it to yellow. Oops, change it to yellow. So it says negligible. So we all know that they will hit, even if it's heavy, even if it's massive, less mass, it will hit the ground at the same time because of acceleration due to gravity. Now we have concept 1, concept 2, concept 3. Put it all together in a cohesive sentence or cohesive paragraph. And the next page, next slide, present a cohesive explanation by putting all these 3 concepts together. And I will read it to you. So here's the next slide. Here's an example response that expected from you. The dart with the smallest mass will go the farthest since it will have the greatest horizontal speed or velocity as it leaves the tube, while the time of flight and height of drop remains the same for all darts irrelevant to its mass. Okay? Again, while the time of flight and height of drop remains the same for all darts irrelevant to its mass because of the law of gravity. The dart will experience the same initial force while inside its tube as it travels the length of the tube L. Newton's second law of motion states that net force is mass times acceleration, or acceleration is the net force divided by mass. Therefore, the smaller the mass, the greater the acceleration, resulting in a greater speed as the dart leaves the tube. The mass of the dart is irrelevant once the dart leaves the tube because falling object will reach the ground at the same time when released from the same height regardless of the mass. Okay. So combining all those 3 principles together to come up with an explanation. And here's my claim. The dart with the smallest mass will go farthest since it will have the greatest horizontal speed as it leaves the tube. And the rest is my explanation and justification using scientific concept. Again, if you didn't get as we reach this point, you may always go back to the previous slide, previous page of the video, and then you can listen again or go over what was explained in that section. So the next, well, this is the question. So of course, you will select small mass. So this is your justification is on the previous page. So now let's go to question B. Okay, so question B. On the internet, a student finds the following equation used in a similar lab situation. X is equal to mhg over fg L squared. Regardless of whether this equation is right, to find the horizontal distance is correct. Okay, I'm sorry, let me just read it. Regardless of whether this equation to find the horizontal distance is correct, does it agree with your qualitative reasoning in part A? Your qualitative reasoning in part A doesn't have any data yet. In other words, does this equation for x have the expected dependence as reasoned in part A? Yes or no? So let us write down the conclusion. So according to our conclusion in question A, the smaller the mass, the farther the dart will travel. Okay. Now, there is something wrong about this equation. Okay, there's something wrong about the equation. Now, we'll find out if the equation prove, will it actually prove our answer from letter A. Okay, so let's analyze the equation. Again, I mentioned it earlier. If all the variables in the equation remains constant, okay, so let's say the mass will not change. I'm sorry, constant except for the mass. Let's say height will not change. G is the same. Force is constant. G is the same. L squared is the same. Hmm. Right away, I know that there's something wrong with the equation because I can actually cancel my G. However, that's not a question. Question, does it justify question A? Will it be good enough to prove that your answer for question A is correct? So we can just isolate M. So your M is right here. So let's isolate M and have it by itself. Okay. So I have it by itself. Okay. Now let's change this bunch of numbers to a constant letter K. So we don't have to change it. So now we can have an equation X equals M times K, where M is the mass of the dart and K is are the constant variables that will not change in the equation. So now let's create a table where M is our independent variable, something that we manipulate, and then X is our sorry, is our dependent variable. So if you change your M, if you put 1, what's the value of X? Oh, 1K. If I change M into 2, I will have a value of X equivalent to 2K. If it's 3, it's 3K. Oh, so the trend already shows that this is in contrast to what our answer to letter A is. The equation confirms that the mass increases, the displacement X increases, displacement increases. But according to our answer to question A, the smaller the mass, the farther the dart will travel. So this is already in contradiction to what we answered to letter A. So in the next slide, I will present an example of a paragraph that you may use as your guide to answer a question like this. From the response in question A, if the mass m decreases, it should make the displacement x increase. However, in the equation, the mass is in the numerator. With the mass as a numerator, it will result into decreasing the mass will decrease the displacement. The mass should be in the denominator instead. With the mass as a denominator, if the value of mass decreases, then a smaller number is used to divide the number, resulting to a greater displacement. In addition, the units on the right side of the equation does not correspond to the unit on the left side of the equation. Therefore, we all know, or it's already clear to everyone, that the equation in letter B does not support the answer for letter A. So let's move to the next question, next scenario. So another student make a mistake in their derivation and develops the following expression to predict the landing location of the dart. So which means the horizontal distance x. And this equation is F hg, force multiplied by the height times the acceleration due to gravity g, divided by the product of mass and the length of the tube. So without deriving the correct equation, how can you tell that this equation is not plausible? In other words, that it does not make physical sense. If there is more than one reason, if there's more than one reason, make sure you discuss each. Maybe there's more than one reason. But of course, the first thing that you should do is to justify at least one. Okay? Additional points will follow if you justify all of them. But at least make sure you have one in your answer. So answer from question number one. The smaller the mass, the farther the dart will travel. Common sense. Okay, what is the effect of m is the effect if m is a denominator? So from question B, the smaller the mass, the farther the dart will travel. If m is the denominator. But since in the equation earlier, it was a numerator, so it doesn't support question A. Okay, so let me take a look at this problem. The equation x, now m is part of the denominator. Hmm, this might be right now. Let's take a look. So what is the effect if L increases? Now again, we all know the longer the L, the greater the speed, and the greater the speed, the longer the x. Oh, I think there's something wrong about this. It's because L is now part of the denominator. So right away, we can actually look at this. So increase if L increases. So the longer the tube, the dart is given longer time to accelerate, resulting in greater launch speed. The greater the speed launch, the farther the displacement. I just mentioned it earlier. I just repeat myself. So let me just go to the next page to analyze the equation. So those three concepts that we must understand. Now, as you are watching this video again, you can go back, pause, and look and listen to the explanation. So now, let us explain how this equation actually contradicts letter A. Not about M now. M is correct, so the location of M is correct. Some of you might just immediately jump into the conclusion that this equation is correct because of M. Because we said in question B, M should be in the denominator. Now this equation is in the denominator. However, how about L? If all the variables in the equation remain constant except for the tube length, again, tube length. So this time we have L. We can just replace all the other variables to K, and that K creating this kind of equation. X is K 1 over L. So our independent is L. So if we change L into 1, X is equivalent to K. If L is 2, our value for X is K over 2. So we're dividing it by 2. If it's 3, you divide it by 3. So common sense will tell us that as you increase the L, you actually decrease the X, which is in contrast to our explanation to question letter A. So therefore, the equation confirms that when the length of the tube L increases, the displacement decreases. No, it's not. You're supposed to increase as it increases. However, it says over here that when you increase, the displacement decreases. So it's the opposite. So right away, we all know that this is the opposite effect. Now let's go to the element again, the equation. So now that we were done evaluating L, why don't we check the different variables? Okay, okay, so in the event that this experiment is conducted in other location, let's say on planet Mars, so the acceleration due to gravity is different. So why don't we take a look at acceleration due to gravity? So it will actually So all the variables, let's say G. So let's isolate G. Again, let's change the other one that will be kept constant to K. And all we have to do is just change the value of G. So the equation would yield a greater horizontal distance. So if we change the G, it says that we're going to get a greater X. 2k. X will be 3k. Hmm. So it means that the stronger the gravity, the longer I will stay on air. That doesn't make sense. So the equation will yield a greater horizontal distance if acceleration due to gravity is greater. This is not possible to happen. The greater acceleration due to gravity, or g, will make the object hit the ground faster than lesser acceleration due to gravity. So again, the stronger the g, the shorter the time that you will have to travel. So right away, this will not provide us with a nice explanation. Now, what if we analyze the equation again? So the location of G is already incorrect. So far, let me highlight the equation. G, not possible. L is not possible. M, it's possible. How about the other forces? Or if force is kept constant. How about let's take a look at H. If all the variables in the equation remain constant except for height, let's take a look. X, so let's take a look at this one. So X FG over ML times H. So what if we kept everything constant? So let's keep everything constant except for H. So now the new equation is XK times H. If you notice the pattern, just keep everything as K. Those are going to be kept constant. And just leave your variable that you change as the dependent or independent variable as the only variable that you will have to record. So H, let's take a look at what will happen. So the higher the height, we have K. 3K, does it make sense? So it means the higher I am released, it means that the longer time I will experience. And the longer time I will experience during flight, the greater the x. So it means that location of height is actually correct. So again, let me just repeat the statement that in the equation, in the next analysis of the equation, assuming that everything on the right side of the equation are kept constant except for h, okay, when the object is released. Since the height is part of the numerator, the greater the height, the farther the horizontal displacement x is. This is because there is a greater height for the object to travel. This is one part of the equation that supports the answer for question A. However, the other part of the equation does not validate our answer for letter A. So the next slide will give us a summary of all of this information that we just did, analyzing the equation as one cohesive answer. So if the length of the tube were longer, the dart would have been accelerated longer, and so its horizontal launch speed would be greater, resulting in greater displacement x. So everything is already mentioned. So therefore, we expect L to be in the numerator, which is not. Also, if the acceleration due to gravity were larger, the time it would take the dart to fall, the distance h, would be smaller, which would make the displacement x smaller. The equation as presented indicates that if g increases, the displacement x increases, which does not make sense. Therefore, we expect g to be in the denominator, which is not. So here's your argument, justification to this part of the problem or the question. So letter D, and then we have E and F. So the group of students is given the task, again, experimentally determine the height of the tube using a linear regression analysis. Again, linear regression analysis, the height of the tube. So you're trying to figure out H. The students are able to change the magnitude of a constant force exerted, are able to change the magnitude of the constant force on the darts, but not the length of the tube. So you can change the force, but not L, or the mass of the dart. So once you selected the dart, you are stuck with M. So this is part of your K. You're stuck with F. Of course, we're stuck with G. And then all we have to figure out is how are we going to figure out H with just L? Okay. What quantity should be graphed to produce a linear graph from which vertical height of the tube could be obtained? Let's justify your answer. Calculations or equations may be used in your answer, but calculations alone are not sufficient justification. Okay. So here, my suggestion is to emphasize. So emphasize the use of slope. And for this one, we all know that slope, which is represented by the letter M, use the purple, represented by letter M, is simply rise over run. Okay, so which is rise over run. So rise over run, rise over run. We always hear this in mathematics or in math class, rise over run. Or it is actually the change, okay, the ratio between the change in vertical axis and the horizontal axis. Vertical axis, horizontal axis. So that is your height. So let's replace your slope to height. So this is your height. So it's supposed to be your slope. So that's why you change that slope M to your height H. So now height is actually the change in the vertical axis over the horizontal axis. Now, if you look at your experiment, the equation that they give us, H equals mgx squared over 4FL. Okay, so slope. So this is a slope. So what do you think is your dependent and what is your independent? So in this experiment, we've been trying to figure out the value of x. So, so mass is constant. Again, those are constant. So now let's figure out the value of x. So this is your independent or dependent, I'm sorry. So this is your dependent variable. So this is the dependent. The displacement x is something that we're trying to figure out using this experiment. So x is your independent or your dependent variable. So every dependent variable should always be on the left side of the equation. And that left side of the equation will change into your range. And then all of your dependent or independent variable, again, let me just replace. Independent variable should always be on the right side of the equation. So if I'm going to take a look, so this is your range, which is your vertical axis, and your F, that is your domain or horizontal axis. So we're changing the length of, you cannot change the length of the tube, you cannot change the mass, but you can change the force. So this is our domain, which is your horizontal axis. So this is your domain, this is your range, which is your y axis. This is your domain, which is your horizontal axis, or also known as your x-axis. So on the next slide, it's a cohesive paragraph. Let's explain why is it that x squared is the dependent and f is the independent. So let's take a look. Next slide. So rewriting the equation so the two quantities the student must measure. So you're measuring two quantities. One that is variable, not variable, but independent variable, which is something that you manipulate, or the dependent and independent variables are on opposite sides of the equation. So our dependent should always be on the left side of the equation, while the independent or something that you manipulate is on the right side of the equation. If students graph x squared versus f, the slope of the line of best fit will be the height h of the table or the graph. So if I go to the next slide, which is actually section E, an experiment is then performed in which force exerted on the dart is varied, resulting in the dart traveling various horizontal distances x, which are recorded in the table below. So what's missing over here? X is irrelevant in terms of our graph because according to the equation, it's supposed to be the distance squared. So the distance squared is our, let me just change the color. So this is our x, which is a horizontal distance squared, which is our horizontal distance squared, is basically our y-axis or horizontal axis, or vertical axis, I'm sorry. So this is your y-axis. So this is our y-axis, y-axis, y-axis. So if we take the square of 3.5, that will give us 12.3, 5.5, that is 30.3, 7, that is 49, 8.6 is 74, 10.2 is approximately 104, and 111.1 is 123.2. So that's how simple this section is. Now let's graph this table. So if this is our table from the previous question, so now let's graph this table. So again, which one is our y-axis? Our y-axis is our distance squared. So let's square it correctly. 25, 75, 100. The greatest value is 123. I think 25, and each one is 5, 10, 15, 20, 25, 30, 35, 40 to 50. And on the y-axis, on the x-axis or your horizontal axis, that's your force. The maximum value is 2, minimum value is 0.2. So I think 0.5, 1, 1.5, and 2 is a good scale for this experiment. So let's just graph it. So when my force is zero point 0.2, let's say it's right here. Okay, so let me use my highlights. So right here, so that's 0 0.2. Let's move up. The value of my x squared is 12.13. So it's somewhere along this area maybe. So let's plug it in. And then how about the next dot, next dot, next dot, next dot. And then let's draw a line connecting this place over here. And then this is our table. So right away, this is our table, and you get full credit. It shows that you know how to draw a table. It shows that you're able to graph the table. Sorry, identify which one is your x and y axis based on the data that is already presented. Last part. So here, last part. Here's the equation. X squared equals 4HL over mg, kept constant. So these are kept constant. So we are just varying this bad boy over here. So if the slope is m, and that is the change in vertical axis over change in horizontal axis, but we all know that the vertical axis is your x squared right here. So x squared and force is over here. However, it says delta x over delta x squared over delta f because it says change in vertical axis or delta vertical axis over delta horizontal axis. So all we can do is rewrite the equation as delta x over f, if I'm moving this to the other side, over is equivalent to 4HL over mg. Again, this is where most of you made a mistake in your solution. You are applying the formula instead of applying the concept of slope. Concept of slope, you must use two different dots, a change, a rise over run. So letter F, this is the graph, and I decided to use 2 points. Let's use this first point over here. This is my first point, and here's my final point. So that will be my initial, that's my final point. So again, from the equation on the other side, delta x squared over delta f is equivalent to 4HL over mg, where the mass is already here and L is right here. So this is my mass M, and this is my L right here. However, our delta x squared. So what is the value here? What's my x and y coordinates? So right away, we all know that my final is somewhere at 75 minus 25. Right here, it's 1, 1.1, 1.2 minus zero point 0.4 because this is 0.1, 0.2, zero point 0.3, 0.4 for my initial. So that's why the difference between the final and the initial. And then just for the sake of showing the units, so 4 times h times 0.35 m, which is your L from the equation, 0.02 kilogram is your mass, times 10 meters per second squared as the value of g. Now, simplifying it further, it will give us an answer of 8.75 meters. So far, this explains the solution to the problem or the assignment that was given to you before you went on break. Please use these slides, use this video for you to study and to come up with some solutions to future assignments, as there is a trend. It's the same pattern that you use, same skills. All you have to do is change what topic we're learning. And what's the beauty of having open notes? Now we have notes available for you to see and take advantage of it. Just make sure you organize as you look at the notes. If you don't have the capability of printing, write it down on a sheet of paper. Solution, step 1, step 2, step 3. And as you write it down, listen to the explanation that I'm giving you. Again, folks, thank you for listening and good luck on your next lesson. Hope this helps explain the solution to the assignment that was given to you. See you next time.